And so now we're back with part two. And so we're back to what is a key, right? So a key is a secret code that is used by a cryptographic algorithm. So it's going to provide instructions that are going to result in that functional output. Cryptographic algorithms themselves are generally known. It is the secrecy of the key that provides this security that we desire. So the number of possible keys that can be used with an algorithm is known as key space. Those were part of the definitions we looked at earlier. And a key space is a large set of random values that an algorithm chooses from when it needs to make a key. The larger the key space, of course, the more possibility for different keys, hence it's more secure. So if an algorithm uses a key string of 10 bits, it's going to result in a key space size of 2 to the 10th power, or over 1,000 possible values. And so the longer keys are harder to break, but they also require more computational and processing power. So there are trade-offs being made here. And so two factors have to be taken into consideration when deciding upon the key strength from a policy perspective: the desired level of protection and the amount of resources available, and it's a balance. And so keys then are broken down into symmetric and asymmetric. A symmetric key uses a single key for two parts, often referred to as a shared key, right? It will encrypt and decrypt the same key. That's why it's symmetric, or the same. Because the keys are shared, symmetric algorithms can't be used to provide non-repudiation or authenticity, right? Because you're sharing the keys. Who knows who did what? The most well-known symmetric algorithm is DES. And the strength of the key is that symmetric keys are computationally more efficient. The weakness of symmetric algorithms is just in managing the key. I've got to pass the secret key along. That creates an insecurity for me. Now, asymmetric cryptography is also known as public key cryptography, right? And what this is going to use two different mathematically related keys known as public and private keys, whereas symmetric is using a single key for both encryption and decryption. Asymmetric is going to use public key and a private key, one to encrypt and one to decrypt. And so the private key never leaves the owner's possession. You own the private key. You never, ever share it. Where the public key, heck, we give that out freely all the time, put it on a server, anybody can get it. The public key is used to encrypt the plain data or to verify the digital signature, but you need the private key to decrypt the cipher or to create the digital signature, right? We're going to look at pictures of that. It has advantages. It's scalable. It has a secure key distribution. It's efficient, but it is intensive in its computational resource demand. So that's the trade-off there. Now, here's a picture of symmetric key encryption. So Bob, he has a key. The keys, notice, are the same. Alice has the same key on the right. And so Bob writes a message, uses the key to encrypt it using the algorithm. The ciphertext is transmitted. Nobody can read it. And then it is decrypted using the same key and converted to plain text so Alice can read it, right? And so that's how that works. I thought that picture might be useful. And so with understanding symmetric and asymmetric algorithms requires this as a starter, right? The larger the key space, as I mentioned, the more keys that I can create. So, for example, I mentioned that an algorithm with a 256-bit key space has 2 to the 256th power of possible keys. And so the more random keys that can be created, the more difficult it is for hackers to guess which key was used to encrypt the data. So simply put, the crypto system converts between plain text and ciphertext, and if the key isn't protected or if it's easy to hack, the hacker will be able to decrypt the message, right? So that's kind of an understanding between the two. Now, there's a formula in symmetric cryptography. There's a formula to determine how many keys you need to make, and that formula is n times n minus 1 divided by 2. You'll often see that formula when discussing communications channels also. Here is a one-slide summary of the definition of symmetric, asymmetric, and then we're tying it then to hashing, okay? So understanding symmetric and asymmetric algorithms, which we have defined now, we add hashing to this general summary. So again, symmetric encryption uses the same key for both encryption and decryption. Asymmetric encryption uses two different keys, the public and private key, and one is used to encrypt and the other to decrypt. And the hash function accepts the input of the message of any length, and it creates this value, and through a one-way operation creates that value, that fixed length output. I've also mentioned that algorithms have been modified over time and strengthened, right? The larger the key size, the more secure, right? So for symmetric algorithms, there's kind of a picture of the types of algorithms. It's that AES is AES, DES, 3DES, 2FISH, BLOWFISH, RC4, and RC5, for example. AES is the current standard. Now, for asymmetric algorithms, here's just a few of them. RSA, Diffie-Hellman, and elliptical curve cryptography, ECC. Just to kind of expose you to that. Not really trying to get too deep. Now, talking about PKI then, or public key infrastructure. So this is the framework that serves to create and distribute and manage and even revoke those public keys that we talked about in asymmetric encryption. And so it's made up of multiple components, a CA, an RA, client nodes, and digital certificates, for example. So the CA, the certification authority, this issues and maintains the certificates. And once you have a CA and create the certificates, it's going to sign, it's self-signing its certificate. You generally want to take a CA from a policy perspective offline, and because you've created subordinate CAs who will actually do the work. You never want your CA being hacked. So once you've created the signatures from the CA, then you create subordinate CAs and you take your CA offline, I think is a good practice. A registration authority, these are largely administrative functions, but they're very important because they include identifying users and their organizations. So it renews certificates, and it can even revoke certificates. So when you request a certificate, the registration authority is going to do those administrative tasks to make sure that you should have one and that it's not been revoked. A client node are the interfaces for the users and the devices and the applications to even access these PKI functions. And the digital certificate itself, this is the centerpiece of it. It's used to associate a public key with an identity, like a server or a user, or even in code signing, right? A code signing certificate, a domain certificate, right? You could use it to, that entity could be any number of things. And so the certificate holder's public key will be on it. There'll be a serial number for the certificate. It'll have a validity period. If you have a unique name like the server, it may have that. It'll have the digital signature of the certification authority or the issuer and the algorithm itself, right? So kind of interesting. Now, so we want to protect cryptographic keys, right? Because if somebody gets a hold of them, they can read our products. So it's a useful cryptographic system is really entirely dependent on secrecy and management, whether it's symmetric or asymmetric. So keep that in mind. I think I mentioned that earlier. So this is so important, actually, that NIST has published 3 documents devoted to cryptographic key management. SP 800-67, that's recommendations for key management, amongst others, right? So keys are analogous to the combination of a safe at this point. And so poor key management will easily compromise strong algorithms, right? So key management is critical. So the book on page 314, 315, it lists some best practices. You want, for example, the key length to be long enough to provide protection, that the key should be transmitted and stored only by secure means, that key values are random, and the full spectrum of the key space should be used, that keys should be backed up, right? Backed up. That's a key escrow. And so, however, multiple copies of keys are going to increase the chance of disclosure. So you don't want to over escrow, right? So the key should be properly destroyed when you're done, and they should never be presented in clear text. Key management, like I said, is important to policies and standards, which is this class, and so should be included in the policy documents along the way. Now, the digital certificates say it can be revoked, and that can happen in a couple of ways. There are lots of reasons to revoke, right? Maybe there's a fraudulent certificate. Maybe somebody else is impersonating another. Maybe somebody was fired or let go. You want to revoke the certificates. Any number of reasons, right? So there's a built-in defense against the fraudulent use of certificates, and that's called certificate revocation, or certificate revocation. So the CA, which issues a digitally signed certificate, it will distribute a certificate revocation. And so your application, before granting access through the certificate, should check the revocation list. Now, that's not always up to date, so a faster way to do this, and browsers should be configured from a policy standards perspective to use the OSCP, or Online Certificate Status Protocol, and that's a more up-to-date revocation list. So that was cryptography. I hope you enjoyed the time together, and I will see you all online. Thanks.